Hello students, so in this lecture I will talk about exhaust pumps and gauges. Now when we talk about high vacuum, this has a very important role in modern development of science, like it is used as in the uh, manufacturing of electronic valves. Then X-ray equipments, in a certain branch of chemical industry now, and etc. Vacuums are very important, like in many characterization techniques, like if we talk about scanning electron microscope, then transmission electron microscope, or in systems like sputtering unit. And etc. Whenever we need a system which is having less amount of impurities, or we want a system where we don't want any scattering with air molecules, no collisions with air molecules. They do in fact use high vacuum. Now, now, first to in a high vacuum management, the pressure is first reduced to 1 millimeter of mercury. This initial condition, and this is done by means of uh, backing pump, and by backing pump we mean a rotary pump. And it's basically an oil pump, and after this 1 millimeter of the basic initial vacuum is reached, then we use higher pumps like molecular pumps, so turbomolecular pumps, or diffusion pumps to take this level of pressure to say 10 to the power minus 4 millimeters, or 10 to the power minus 7 millimeters of mercury, and we reached ultra high vacuum. It's called, these vacuum pumps, and in this range the pressure is called high vacuum, and the step further is called ultra high vacuum. This stands for the ultra. To achieve this ultra high vacuum, we use pumps like titanium sublimation pumps, TSP stands for titanium sublimation pump, and we get a temperature of 10 to the power say minus 10 or even higher millimeters of Hg. Now this millimeter of mercury is the unit of pressure in vacuum techniques, and 1 mm of mercury, it is also called 1 torr, after the name of Torricelli. It's called one torr. And now modern techniques, there are modern pumps which can even reduce the temperature of to the power of minus 13 torr. This range, up to this range, we can achieve the pressure or vacuum. Now, how the vacuum pump will perform, that depends upon the speed of vacuum, the speed of a pump. And the speed of a pump at a given pressure is defined as, at a given pressure, the speed of the pump is defined as the volume of the gas exhausted per second so then right is mathematically is as S is equal to minus dV by dt. V is the volume, and this is the rate of change of volume, and since it is decreasing with time, so we have a minus sign. And so this is the volume of the gas. Now it is of any enclosure at any instant. So in an enclosure at any instant. Now if we assume that the temperature is constant, so we're using Boyle's law. It says that P minus PO into V is equal to V plus dV into P minus PO minus dP, where PO is the limiting pressure, P is the pressure of the gas at any instant in the vessel to be evacuated, pressure of the gas at any instant in the vessel to be evacuated, and V is the volume of the vessel. Now, this Boyle's law, this equation can be written in a different form as P minus PO into dV is equal to V dP. We actually are neglecting this product. We are neglecting dP dV, change in pressure into change in volume, because it is very small, so therefore it's neglected. So further, if we proceed, then from here we can write dP as equal to P minus P0 dV by V, or we can write dP by dt as equal to P minus P0 by V into dV by dt, and we have said that S is equal to minus dV by dt, the speed of the pump. So using this, we may write the dP by dt is equal to minus S P minus P0 by V. So if we now integrate, we can even write it as S by V into dt is equal to dP divided by P minus P0. So we put integration. So this is from time t1 to time t2 to instance, and this will be then equal to, so the minus sign. The integration from P1 to P2, where P1 is the pressure at time T1 and P2 is the pressure at time T2. So we get S by V T2 minus T1 as equal to log exponential p1 minus p0 divided by p2 minus p0, and it is equal to 2.303 log 10 p1 minus p0 divided by p2 minus p0, or we can write s as equal to 2.303 v t2 minus t1 into this quantity again here. Now if we assume that this limiting pressure P0 is very low, so we can neglect this one also. So we get S is equal to 2.303 V T2 minus T1 into log 10 P1 by P2, and this equation is known as the Gates equation. This is the Gates equation. So if we move further from the Gates equation, we can write log E P1 by P2 is equal to S T2 minus T1 by V, and right is equal to S by V into T, where T is equal to T2 minus T1. So we have write P1 by P2 as equal to exponential minus S by V into T. Now if T is equal to V by S, let me volume divided by the speed of pump, then P1 by P2 is simply equal to 1 by E, and which is equal to 0.37, or P2 sorry, it should be P2 by P1. So P2 is equal to 0.37 P1. So what we can say is that the during the time T is equal to V by S, this is the time, the pressure reduces to 0.37 P1. That means we consider this as the initial pressure. So at this time, where it is V by S, the pressure is the instant pressure is 0.37 times the initial pressure. So, like speed, the another property of the exhaust pump is the conductance of a tube. The tube from which the gas is through which the gas is flowing. Now, if we assume that if capital Q is the volumetric flow rate of a gas through a tube, due to the pressure difference, dP is the pressure difference. I'll call it as delta P, not dP. Delta P is the pressure difference. So I'll call it as the pressure difference. Then the conductance of the tube is given as C C is equal to Q by delta P. Now this Q is equal to minus P dV by dt. So we can rewrite this above equation as Q as equal to delta P divided by 1 by C. Now if we compare this one with the electrical conductance, and we compare this, we draw an analogy. With electrical circuits, and we write that delta P is equivalent to the potential difference and volumetric flow rate Q, if we consider this as the current, so then this value, this becomes the electrical resistance R. So like the resistance can be arranged in series and parallel, so we can simply write for series, we know that the total resistance is the sum of the resistances arranged in series. So similarly, we can write 1 by C is 1 by C1, but it is equivalent to the capacitance by C3, and for this for the series, and if we arrange in parallel, then it's quite the opposite. Then C is equal to C1 plus C2 plus C3 dot dot. So this is how the conductance behaves. Now the conductance again of a tube depends upon its diameter. C is proportional to uh, d cube. Now, since the speed of pump and the conductance of pump they have the same dimension, so the relationship for series and parallel will also be applicable to the speed of the pump. So it means that uh, if a pump having a speed s is we connected to a vessel through a tube, uh, through a tube which is having a conductance c, then the effective speed of the pump, so then the effective, so it implies the effective speed of the pump will be 1 by s, uh, let's say is called this one as s1 is equal to 1 by s plus 1 by c. So we can also say that the effective speed of the pump or the effective rate of pumping is large when the conductance of the conducting tube is large. So the effective pump speed is large when the conductance of the tube is large. And since the conductance is depending upon the diameter, since it is proportional to dq as previously said, so to get a higher pumping rate we need to increase the diameter of the tube.